Hello.
You and me, Evald.
Uh, Looks like it.
It's fine with me. Well, not really. Those other people. This is not a class you can miss. It's too much stuff to figure out in too short of a period of time.
Yeah. Did you read the email I sent you by any chance?
I don't think so.
Okay. Well, it's okay. It was just about the question 53, because me and Ben we looked at it, and it was just like on the back of the book it was like answers yes, yes, which is like what kind of calculations we need to do. I mean, I can open the question if you want to look at it.
Yeah, I was asking where it. Yeah.
Oh yeah, I just tried to do that one really quick. I'm not sure if I did it the right way, but
Let me take a quick look here. 53. Yeah, and we need to do one thing today that we didn't really get to before. You did say 53, right?
Yes. Because it include, I think, the question 52 as well.
Right. Yeah, the main thing with that question is just the fact that if you're pushing on something, if I'm trying to get this to rotate around this point right here, so I decide I'm going to push on it like it's a wrench, the best thing you could possibly do is push perpendicular to it, as I'm doing right now. So if I was pushing down right now with 50 pounds of force, or pulling down with 50 pounds of force, the fact that I'm pulling or pushing perpendicular means all 50, because the distance to the point of rotation is always perpendicular. So if I turn it over this way and push it 50 pounds, that's kind of stupid, because that has a horizontal component which is contributing nothing, because it's pointing straight at the point of rotation. In other words, if I pushed from here, it's not going to want to rotate at all, because there's no distance. I mean, I might push at 50 pounds, but I'm pushing directly toward the point of rotation. Therefore, it doesn't want to rotate at all. Now, if I change it to here and push it 50 pounds, it is going to want to rotate. But the problem is the only part of that 50 pounds that counts is the 50 pounds times the cosine of the angle that turns it into the perpendicular version. So then I'm getting less force. My distance is still this entire distance, but now my 50 pounds might only be 30 pounds. And so it's not going to want to turn as much. So perpendicular is kind of your best bet. If you're pulling on a wrench, you want to push perpendicular, so all 50 is perpendicular. Does that make sense? I mean, that's kind of the issue with that question. And the little cheater pipe thing is really cool, because if you extend it out, now you're able to push way out here. So your same 50 pounds times a much longer distance is now much more torque, and now it has much more desire to want to turn as a result. Does that concept make sense? And this class, we always fall behind every day. We didn't actually even talk about rotation around an axis, which I want to start out with today. But to that end, I want to give you some good news, which is I'm going to show you something today about 4.6. So I'm going to teach it to you, but we are not going to do it. So make a note in your syllabus to go in there and get rid of 4.6. I'm going to do question 77 for you in class, so you at least understand, like, oh, okay, I see the concept there, but then let's not practice it. And I'm not going to put it on the test. So no 4.6 assignment. Now 4.5, we didn't do a question like that. We were kind of ran out of time. And so if you feel the need to change your work or whatever, if you already sent it to me after I show you one example of that, then please do. But what I want to show you is, I guess I'll just get over to, I want to show you what rotation around an axis looks like, because again, that's related to that same concept. When you turn the wrench, does it make sense the axis is pointing straight towards you that you're trying to rotate around? So if I'm pulling downwards in this direction, the rotational axis is right over here. When you rotate a nut or you're trying to tighten a bolt, the bolt is the thing that's rotating. And so that's the axis of rotation. So usually you're trying to rotate around a particular axis when you're rotating something. And so that's kind of what 4.5 is about. And we didn't have time to look at an example about that the other day. Wish I should have left you. I should have left you with, I didn't notice it, if you will. I should have left you saying, hey, we didn't talk about 4.5. So let's do an example on Tuesday or something. So that was a mistake. So let's take a look at this. And you will see a question like this on the test. We are 1 week away from our first test. And I guess I'm just saying this is the most practical. Notice this is not saying let's, and I had to make this problem up myself because I didn't think there was a good one in the book. But notice this time it's determined the magnitude of the moment of the force F on pipe OA. In other words, can you see pipe OA is attached to the wall through that little floor flange thing? And so when you rotate that, that's going to cause the pipe to want to kind of untwist, lefty loosey. You can tell the arrow's pointing left. It's going to want to unloosen it. And so this time it's not the moment around a point, around point A, it's around axis OA. And so I'm going to reference the note sheet that I hope you have printed off just because you kind of need it in front of you. I posted this in my open math for you, I believe, and you certainly will get this on the test. But really, number 5 there, moment of a force around a point, that was 4.4 assignment. But really, number 6 here, which is the last thing that you need to know, is moment of a force around an axis. And notice the difference if you just stare at this matrix that we're taking the determined of versus this one. What's the difference between those two matrices? Notice the R's are the distances unchanged, the forces unchanged, force of X, force of Y, force of Z. The only difference is up here, we kept track of which axis is it rotating around, and our answer wasn't a number. If you're saying rotation around a point, you don't just get a number for an answer. You get the force in the X around the X axis, the force around the Y axis, and then the force around the Z axis separately. But when you go around an axis, then what you're really doing, the only thing you're adding to this is notice these U up here, that's the unit vector, that's what the U's for. That's actually the lengths of axis A. In other words, the unit lengths of axis A. I'll show you what I mean by that in just a second. So what you're multiplying by this time is not just an I that keeps track of, hey, this is the one around the X axis. You're actually multiplying by a number. You're multiplying by a number, by a number, by a number. And notice it's still plus, minus, plus. You're still taking a determinant if you wanted to memorize this. But you're actually going to get a numerical answer. In other words, how badly does that pipe want to unrotate? So we're going to be staring at that formula. So now I got to make that go away. So let's see if we can figure that out for this particular example. Wrong. Right. So I want this to be easy, but notice we're taking advantage of a tremendous mnemonic device here in that matrix because it's just so complicated to figure out desire to rotate in 3D. So let's take a look at this axis right here. I will color it red because we're rotating around that axis. Let's see, what is like, where is that axis? Well, notice it's 0.1 and 0.2 in the X direction. So it's kind of 0.3 over here in the X direction, and then it's 0.4 in the Y direction. And notice it's laying in the XY plane. So it's Z is 0. There is nothing there. It's 0.3 and 0.4. Now, in that formula I just showed you, if we multiplied by 0.3 and by 0.4, does it make sense that would actually change the size of the force? Like, those aren't forces, those are lengths. The reason we're converting that to a unit vector is because the length of a unit vector is 1. And therefore, when you multiply by 1, you don't change something. That's the logic as to why you're multiplying by a unit vector. And the lengths will tell us what that is. So with respect to U, describing the axis of rotation. And again, please interrupt when you have questions. Interrupt, I said. In the X direction, it's, let's see, I guess that's positive 0.3. And in the Y direction, that's also positive 0.4. Wait a second, how do I know that that's positive or negative? I actually got to think about that a little bit. I'm going from O to A. I'm just trying to think, does that matter? I don't think it does. And then because it's laying in the XY plane, it's not, there's no Z at all. It's kind of flat. It's down there in the XY axis. Are you good with that? Does that make sense? So if I do the Pythagorean theorem in 3D on this to see what the hypotenuse is, if you will, then of course I'm taking 0.3 squared plus 0.4 squared plus 0 squared. So I'm just sort of happy. In a sense, I don't have to think of this as 3D. It's in 2D. And you may remember 3, 4, 5 is a right triangle. So this actually comes out 0.5. So that pipe length is 0.5 meters. It's half of a meter long. So as I said, I wouldn't have had to do this in 3D. I just wanted to write it in 3D so you understood if there was a Z, then fine, I'll do it that way. So that means then U as a unit vector is really 3 I guess I better write it this way. U of X then is 0.3 out of 0.5. We're always doing that, right? It's the X divided by the hypotenuse. In other words, that's 3/5 or 0.6, just to get rid of the decimals. So my unit vector is 3/5. And of course, my Y would be the unit in the Y direction would be 0.4 divided by 0.5, which is 4/5. And since there was no Z, there is no Z. So this is my unit vector. Now we're multiplying, we're doing the same thing we did to find the force around a point, but we're multiplying by these terms, not X, Y, and Z, or I, J, and K, like the other formula. We're multiplying this by 3/5 and 4/5. Now, collectively, does it make sense the magnitude of that unit vector is 1? That's why we did this. So by multiplying by 1, we're effectively not changing the force. If the force is 10 pounds or whatever, or the moment is 10 foot-pounds, we don't want to multiply by 6 and make it 60. We want to multiply something that doesn't change its actual size. And so what we're really doing is taking that force and multiplying it by numbers this time instead of just by I, J, and K. That's the only difference. So there's my unit vector ingredients for the top of my matrix. But then let's see, what else did I need? I forgot. I got to go back and look. I can't, this is too complicated just to kind of memorize. I got to think about this a little bit. So now let's see, what's this R of X, R of Y, and R of Z? Those are the lengths from any point on axis A to any point on the force vector. So those are just distances, lengths. So stare carefully at this note sheet, because again, I'm staring at this right now because I have to, like I don't have this memorized. I got to think about this. Any point on axis A to the force, not the other way around. It's directional. It's from the axis, just like it was before, from the point 0 up to the force. It's the same thing. Okay, that's right. Now I remember. So how far is it from the bar OA to that force? Would you agree that there's two places on the force that I know where I am? I know where I am at C, but notice it's also pointing at D. So I could go from O to D. I could go from O to C. I could go from A to D or A to C. Any of those would be okay according to that note. Do you agree with that? The question is how far, all I'm really doing here is how far is it from the axis to the force? I'm going to say O to D. Notice it's O to D, not D to O, because if you screw that up, then you get the signs backwards. So O to D would work, O to C would work, A to D would work, and A to C would work, apparently. So my note sheet was very careful to say any point on OA up to any point on that force. And I know a lot here. So I have all these choices. Now we could stop and think, well, which one's the easiest? That'd be fine. For no good reason, I'm just going to choose A to C. And part of my reason for choosing that is, does it make sense that A to D looks hard? I mean, just at a glance, like A to D, I don't have any clear dimensions from A to D. Are they on there? You bet, I could figure them out. But it looks like A to C is super simple, doesn't it? Because it's like from there to there. Again, it's from A to C. So what is R? What is that distance in the X direction going from A to C? Somebody blurt it out.
Negative 0.2 meters.
Yeah, X is this direction. That's the 0.2, but you're going backwards. So what Ben said is exactly right. Negative 0.2 meters because I'm going backwards. What is my distance in Y? How far am I going in the Y direction to get to C? None. Do you see that? Didn't move in the Y direction at all. So in a sense, I kind of went over X and then how far this way? Well, I didn't go anywhere. I stayed right there and then just went up. So that's actually nothing. And then in the Z direction, I went up 0.3 meters. And again, the Z is up there. So up is positive. So that's a positive 0.3. So there's my, if you will, my R matrix or my R vector. I could choose to write it that way if I wanted. I could say R as a vector would be negative 0.2, 0, and 0.3, and it would be good form to stick meters out here, just like a minute ago. It'd been good form to for this back here to put meters as well. That U vector was actually meters. Lastly, I've got to get all my forces. Let me see, how did that work again? Forces. Oh, darn. Force in the X direction, force in the Y, and force in the Z. I got to break that up myself. Cartesian components of the force. Dang. Why do I say dang? Because in this problem, I was given 300 newtons of force, but that's not in its components. That's just pointing off in space somewhere. And so I got to break that up into its component parts. And I'm going to do that using, again, kind of the unit vector concept, a proportion. So make sure you understand that force is pointing from C to D. So those dots that I made on there that were blue, very important. The force starts at C and it aims at D. And so what we got to do is come up with all the distances. How do you get from C to D? And that's not obvious, right? I mean, I got to stare at this a little bit. This is a harder one. You got to stare at the picture. And again, you got to stay parallel to the axes. How do I get from C to D? Well, switch colors. Look at the forces. Well, let's see. How far is it in the X? So I'm staring at very particular things right now. I'm looking at X. I'm looking for, parallel to that axis. What measurements do I have that are parallel to that axis? I'm tempted to say 0.2, but does it make sense that if I go across, that C is not 0.2 away? What do you gotta see? Somebody help us out here. What dimensions are you looking at that tell you how far this is in the X? I find this tricky.
Well, you can see that there's 0.5 meters in the X back there.
Yeah.
D. So you can subtract what you see over there from what's over there.
That's exactly right. So I'm at C. Where is C? C is at 0.1 meters. So you're 0.1 meters in already to C, but D is at 0.5. So you're a total of 0.4. Is that positive or negative? Well, it's collectively pointing toward X, so it's positive. So let's see, how am I going to write that? I'm going to write that to myself. Let's see, CD. I'm going to say CD from C to D is 0.4, 0.4 in the X direction. How far is it in the Y? Again, you got to stare at this figure a while. You got to stare at anything that's parallel to the Y axis. There's 0.4, that's parallel to the Y axis. That's the only one I see. Well, that's actually good news. It's 0.4. Well, that's how far it is. It's 0.4. Okay, great. It's 0.4 in the Y direction. Is that positive or negative? Well, because it's going from C to D, that's backwards from Y. So that's negative. And finally, Z. What is it in Z? Again, I'm looking parallel to Z. There's a 0.3 there. There's a 0.5 there. Hey, that's the only ones, 0.3 and 0.5. Well, if D is 0.5 up and C is 0.3 up, then that means the difference of those is 0.2. So it's 0.2 up. So that's positive. Do you agree with that? So we're using a proportion to get this. Or you might think of it as a unit vector. I've been kind of using the proportion idea. It's the same thing, but I'm going to do it as a unit vector this time. So then what is the magnitude of CD? Well, I've got to square all of those and square root them. Notice I left the negative for Y out just because I'm afraid if I type in negative 0.4 squared, I'm going to get it wrong. So 0.4 squared plus 0.4 squared. Idiot. 0.4 squared plus 0.2 squared. I got 0.36. Wow, thank you, book problem. 0.36. When I square that, I actually get 0.6. So that means the unit vector of CD could be written as 0.4 divided by 0.6, which would be better to write as 4/6 or even 2/3, which I'll switch in just a minute. And then I got to be careful not to lose the negative for this one, negative 0.4 over 0.6 and 0.2 over 0.6. So better would be unit vector for CD. And maybe I should be writing that over the U. let's see, that'd be 2/3. This is negative 2/3, and this is 1/3. So the point is, those are your proportions. And so if you take your force, which was 300 newtons, and you multiply it by that vector, 2/3, negative 2/3, and 1/3, you get 200. So this is now your force vector. You get 200 in this direction, negative 200 in that direction, and 100 in this direction. Why does that look wrong to me? No, that's right. And these are newtons. So I've now got every ingredient I need to stick in that matrix. Now, the reason I thought it was wrong there for just a second is I was thinking Pythagorean theorem. If I did Pythagorean theorem with 200, what should I get? If I got that right? I should get my 300 back. I mean, the actual force is 300, but I just broke it into its X, Y, and Z components. And so that's what the unit vector or those proportions are doing for you, is figuring out what percentage or what proportion of that 300 is going in each direction. And I'm using the lengths that define the direction it's aiming to help me do that. So that's why unit vectors are cool, because effectively what you're doing is multiplying 300 by 1. So you're not changing the 300. You're just partitioning it out to how much in X, how much in Y, and how much in Z. And so my first thought was, wait, that's going to add up to way more than 300. But then I forgot, oh, that's right, we got to square root it. So that's 400 plus 100, 4,000 or whatever. But oh yeah, that'd be 9. The square root of 9 is 3. Okay, yeah, that does work. So there's all my ingredients. Wow, this is time consuming. So then I can say, according to my note sheet, which I don't want to flip to, but I do want to look at, where are you? How do I write this? Well, I'm trying to find the moment. What am I trying to find here? The moment, get bigger. The moment around, the magnitude of the moment around pipe OA or axis OA. So I'm going to write that as like this, the magnitude of the moment around OA. It's not the magnitude around O. That would be the rotation around a point. It's around an axis, and I define the axis by those two endpoints. That's how you, in geometry, it's like segment OA. And then my large and intimidating matrix then is to rewrite all of those radiuses, which were 3/5, 4/5, and 0. And then all my distances as to how far the axis is away from the force, negative 0.2, 0, and 0.3. And then all my forces, 200, negative 200, and 100. And then take the determinant of that matrix, and that's going to produce a number. Now, again, can you at least picture what this is accomplishing? You're taking the force of 200 in the X direction, and you're multiplying it by how far that is away, how far that force is perpendicular away from our axis. All this is forces times distances. That's all it is, a bunch of, but there's just a ton of them. That's the problem. So let's see, let's use our mnemonic device. So I'm taking this row and this column out, which means I'm taking 3/5 this time, times the diagonal multiplication, 0, always minus, and then 0.3 times negative 200. Notice how easy it would be to screw up the signs there. It's actually minus a minus, so that's going to be a plus. That takes care of that one. Next, 4/5. What's important to remember about the 4/5? That's on my note sheet, but if you're memorizing this, what's important about the 4/5?
Negative.
Negative. You change the sign of it. Again, I'm coming back and crossing out this row and this column this time. So that leaves 4/5 times, let's switch colors just because this is going to get confusing. So I'm multiplying 0.2, negative 0.2 times 100. It's always minus, and then 0.3 times 200. And then back to plus, and then, oh, cool, force Z is 0. So I sort of don't care what's sitting in there. That's great. Awesome. That'll save me some time. So just to make sure I don't screw up, I'm going to at least go a little slower. So let's see, 3.3 times 200, that's a negative, and a negative, that's a positive, so that'd be 60. And then minus 4/5 times, this is a little worse, type everything in just so I don't screw it up. Negative 2 times 100, negative 0.2 times 100. I know I can do that in my head. Minus 0.3 times 200. I got negative 80 for that. But I'm also staring at my calculator to make sure I actually typed what it said. It looks like I did, negative. So now I can actually multiply that out and answer it. So I'll do this in my head. 60 divided by 5 is 12. 3 times 12 is 36. 80 divided by 5 is 14. 14 times 4 is 56. I probably shouldn't trust myself. That's 16. It's a good thing I didn't trust myself. 80 divided by 5 is 16. Times 4 is 64. So that just came out 100. What was my units? I was a little footloose and fancy free about that. What were my units?
Be Newton meters.
Yeah. Now, because our forces were newtons and our distances were meters. Is anybody bothered by this? Isn't the units for this row meters, and this row meters, and this row newtons? So wouldn't it be meter newtons?
Well, that first row is a unit vector, right? So I think the meters cancel out there and just be regular.
Good job, because when you look back here, wasn't it 0.3 meters divided by 0.5 meters? So the meters actually cancel. So that top one is actually unitless. That's what a unit vector is really doing. It's cleansing it of everything. So if you are bothered by it, no, it's really nothings times meters times newtons. So it is Newton meters if you follow the units through it. So now you can say that's how badly the pipe wants to turn. And does it make sense that now you can kind of know, is that going to turn? Is it not going to turn? Is that enough force? You see how you've got to kind of lean on that mnemonic device to get this right? Like, man, 3 dimensions, this is really, but I would say as a takeaway, that's one of the biggest things you need to be able to do right there, because it's hard. It's a 3 dimensions, because real life's in 3 dimensions. And you got to know the resulting, and that's really, and I think the end of this chapter between today and tomorrow is going to really help this all come together for you. We don't have to learn anything new from now on. We're just applying this to interesting questions. So that's the good news. You're done. The note sheet was ended. There's nothing else for me to teach you. We just get to kind of apply and practice and strengthen our grasp of this. Anything bugging you about that before we go on? Really? No? let me just quickly show you where we are going from here with kind of a couple of cool pictures that I stole off the internet from somewhere that I think illustrate kind of what's going on here. Check out these kind of cool home designs. I'll just stick with that top one right there. Isn't that cool? Like, wow, that's awesome, man. Would you like to live in something like that? They got this front porch out there that sticks out, and so you can stand out there, and it's obviously up in the mountains and you're over the top of something. But can you see what we've been talking about here? In the sense that, hey, they got this whole building cantilevered out. And can you see that it wants to do two things? It wants to fall because of gravity. And you can see the pipes are there pushing up to counteract that. So the force down is counteracted with the pipes pushing up. So it isn't moving. Good job, engineer. Statics. You made it not move. But the building is also attached back here. Does it make sense? It also wants to rotate. It wants to sort of cave in this way. So I got to track both of those things. And so I need to know, in this sense, in this picture right here, can you tell that, if you will, the building wants to rotate along that axis right there, that axis of concrete that's holding it up? That's what it wants to rotate around. And you as an engineer have got to figure out how badly it wants to do that, so that then you can come back and put these supports in down here and make sure the pipes are thick enough and that they're embedded in cement enough so that it's going to stop that rotation from happening. Again, our problem we just did, we stopped halfway there. We found out how badly this wanted to rotate down, and we just said, okay, we're done. But in the real world, you got to come back and say, okay, now I got to create something that has the ability to unrotate that. I got to make the sum of the moments around this axis here 0. So this pushes up, that pushes down. The sum of those moments is nothing. Hey, it's static. It doesn't want to rotate. That's an engineer's job. And we really are, in many respects, done almost for this entire course, in terms of we just got to get a little bit better at understanding how to pull that all off. Can you see this one down here is even cooler? Because it doesn't even have any supports. And so you might wonder, wow, how in the world? I would have thought there'd be like a pipe over, like a post over here holding that whole thing up. Can you see it here? This awning wants to rotate downward along this axis and fall on that car, but up here is a connecting rod pulling back, keeping that from happening. So that's why you got to calculate moment around an axis, and it usually is around an axis, not a point. So that last problem I just did, I think, is pretty key. How's your brain? Is it okay? Smoking?
I think Aaliyah's audio wasn't working, so that's why she was leaving and coming back. I guess she's not here now, but.
Got it, okay. Thanks for pointing that out, because I'm not always going to see the chat since I'm busy rambling. Let's see. What do I want to show you next? So I want to show you this really quickly, but we'll actually get to it in just a second. So can you appreciate that? Kind of looks like that house cantilevered out over the ground. And so you have this beam sticking out here. And notice I just made up some sort of fake forces, as your book will do. It's like there's 40 pounds pushing here and 52 pounds pushing there and 60 pounds pushing up. And so two things want to happen. This whole beam wants to fall down to the ground, but because it appears to be pinned here, it also wants to rotate down around O. And so we just got to kind of figure out all of that now. You don't need to learn anything new to do that. And also notice this is two-dimensional. Many problems in sort of structural engineering are just two-dimensional. So this isn't near as hard as that matrix we just did. So we'll tackle that in 1 second. What I want to do quickly before that, though, is show you And that's really what we're going to spend the rest of the week on. But because we're skipping 4.6, I want to show you one question in 4.6. And this is why we engineers get a bad name. I'll show you what I mean right now. So 4.6 is, and again, if you showed up late, we're not doing any questions out of 4.6. This is one of the, well, anyway, we'll get there. So let's stare at this. So only an engineer would come up with a name like couple moments for this. This is why we get teased. If you looked online at like engineering memes, they're all negative. They're all poking fun at us for being nerds, which is kind of true, but we also make the world go round. Couple moment, man, how in the world did you get that into an engineering class? Well, watch this in action. This is really the idea here. And you don't need to learn anything new or even this terminology to understand the logic. But let's go figure out the moment around O. You should be able to do that right now. Super easy. Notice all of the distances are given and the forces are perpendicular to them. You don't need a matrix and a determinant to figure this out. You can just do it with pure force times distance. Remember the convention that going this direction we're calling positive, and going this direction we're calling negative. And I just want you to find the sum of the moments. Well, you should say that's super easy. I would take 240, this 240, times its distance. Again, notice that's perpendicular. That force extends down here. That distance extends right there. Those are already perpendicular. I don't even have to convert 240 to its X and Y coordinates. So 240 times its distance of 24 meters. And maybe I won't be lazy. I'll write 240 newtons times 24 meters. And again, the convention is that's negative. So I'll throw a negative in front of it. So we got that. But then notice this is the exact same force. That's why this is called a couple moment. Those two forces are exactly the same. And I'll talk about that in a minute. That would be causing counterclockwise rotation. So that's actually positive. So it's also 240 meters, but it's further away. It's 24 plus 14, 38 meters. You should think, yeah, this is totally easy. There's nothing new here. This is the easiest problem we've done. If you don't blow that, you get 3360. And again, what that means is desire to rotate. So because of these forces, that beam wants to rotate in the positive direction. The forces were working against each other, but it wants to rotate around O in the positive direction. 3,360 Newton meters. And again, we can't stop there. We got to stop that from happening as an engineer, but the whole key is finding the resultant. What I'd like you to do now is redo this problem, except for let's do it around this point right here, point B, which we'll put perfectly in the center, 7 and 7. Recalculate this moment around B. What do you get now? Let's see, you get the same 240, a distance of 7. It's causing positive rotation. So 240 newtons times 7 meters, positive rotation. And then if you come over to this other one, isn't that also causing positive rotation? They're both positive. That's interesting. So then it's 240 newtons times 7 meters again. What do you get? You get the exact same answer. Is that a coincidence? The answer is no. Sometimes couple moments are sort of called pure rotation. Kind of making that language up, but it actually doesn't make any difference. When you have a couple moment is defined as two equal forces parallel to each other. Notice that's happening here. They're both pushing parallel to each other and they're the exact same force. That causes pure rotation. And you want to think about that as, well, like an airplane propeller. It's just spinning around a point. Or if you grabbed one of the illustrations in your book is like grabbing a wheel and you're gonna, not a car wheel, but like a wheel that opens a gate or something. Does it make sense? You grab it with two hands and you push up with this hand and pull down with that hand simultaneously. And because they're your arms, you kind of have the same amount of force. And so you're sort of pushing up with 10 pounds and pulling down with 10 pounds and turning it simultaneously. And it wants to rotate, well, around that point B right there, around the center. So like in this case, no matter what point you pick, we started with O, which is the natural point to pick because of the picture, but it actually doesn't make any difference. As an ultimate shortcut then, which again, you don't really need to know this for any problems we're doing, but this is why it's in the book. As a shortcut, you could actually sort of think of it as, well, what if we put the point right there, point C? Does it make sense? This 240 right here would produce no rotation at all because it's pointing right at the point. And then the other one would be all of it. So then it'd be 240 newtons times 14 meters, which is still 3360 Newton meters. It's like the same answer no matter what you get. So as a shortcut, if it's a couple moment, you really can just take the force times the distance. And that's not written very clearly, but it's the same exact force. So just write it down once, not twice. And then figure out what is the distance between them. Do you see what I'm saying? Because it doesn't make any difference what point you pick, you're going to get 3360 anyway. Interesting. Okay. Let's see. Let's try to do this question then really quick out of the book. So this would have been one of your assignment questions, but now you're not doing any questions out of 4.6. So let's just do this one quickly using that cool shortcut. Notice it says two couples act on the beam. First of all, do you agree that that's actually happening? And they're telling us here that this is 150 and this is also 150. Do you agree that the two forces are parallel and pushing in the opposite directions of each other? I actually didn't add that to the notes before. So 200 is doing that. But then 150, they're also parallel. Now they're at an angle, so that's a little more complicated. But I'm going to use this shortcut to figure out the resultant moment. So when they say couple, it just means, oh, cool shortcut. Again, you don't need to know anything new to get this right. You could just go. But notice it doesn't say determine the resultant moment around point O, because these are parallel and opposite to each other. It doesn't matter what point you pick. You can pick any point you want. So if I give you this problem on a test before I taught you this, you wouldn't have known what to do because you would have said, well, which point do I pick? Do I pick this point right here to rotate around, or do I pick that point right there? And the answer is it wouldn't have mattered. That's what you just learned. It doesn't make any difference. So let's find the sum of all of the moments. From calculus, you should remember that symbol from Calc 2. And I'm going to use the shortcut and not even pay any attention to any links. And so would you agree that collectively this 200 this 200 times that distance is the shortcut here. And notice that's causing clockwise rotation. So that'd be negative 200, and I'll be lazy this time and write times 1.5. I see that it's foot-pounds, so I need to include that, but I'll just leave that off for now. So that takes care of all that. I'm done with both of those. I don't even care what point it's rotating around. Do you see the shortcut in action there? I mean, that's why this is in the book. Now, the other one's a little more complicated because does it make sense that we don't know what that distance right there is? Now, the question, so what we could do if we wanted to is try to figure it out. But easier would be to do what we've been doing, which is to break these into their components. So if I split that up from exactly what we just studied a minute ago, and I covered up the 5 there, but would you agree that 3/5 of 150, not 1,500, let's see, if 150 is 30, that'd be 90 pounds are vertical there? You agree with that? And then over here, wouldn't it be exactly the same, also 90 pounds? And would you agree that that's causing, well, counterclockwise rotation, which is positive? So that's plus 90. How far apart are those two forces? Does it make sense? You can see how far apart those are? So rather than find a weird distance, I found a weird force. And now those are 4 feet apart. So I can say times 4 feet. Do you agree with that? And then lastly, let's see, what color haven't I not used? How about purple? Lastly, I've got this purple force right here. Wouldn't it be 4/5 of 150? Which would be 120. And wouldn't this one over here also be 120? And so notice those are parallel to each other. And in this case, I know they're distance apart. They're also 1.5. They're also trying to create counterclockwise rotation. So that means we're calling them positive. So it'd be plus a force of 120 times the distance they are apart, 1.5. That's the sum of all the moments. That's a cool shortcut. Around any point. That's why I didn't say around point O. So you could have got this right before this section had I just said find the resultant moment around point O, and I stuck a point O in there and you would have got it right, but you never would have noticed. Didn't even matter what point I choose. That's the idea in this section. So let's see, negative 200 times 1.5 plus 90 times 4 plus 120 times 1.5. I add all that up and I got 240. I got positive 240. Now I'll stop being lazy and say foot-pounds. So the very fact that it's positive means I have answered the question, but does it make sense? It'd be nice to tell somebody that that's counterclockwise, just to kind of reinforce the logic. And so again, what's that pipe going to do with these forces on it? It's going to want to spin like a propeller on an airplane, kind of around its midpoint. Does that make sense? If you think, I won't write this in here, but if you think of this center of this pipe as being here, like the center of mass, basically these are going to cause that thing to want to rotate like a propeller around that with a desire to rotate of 240 and in the counterclockwise direction. You will not see a question like this on the test. But at least you've seen it. So this is the kind of question you're going to see on the test. Now, would you agree at a glance, this is not a couple moment? Do you see forces that are the same pushing against each other parallel? I don't see that here. You see that occasionally, and then you got a shortcut. But, you know, this is just forces rotating and so forth. Now, you don't need to know anything new to do this problem. Replace the forces acting on the cantilevered beam. Cantilever means it's sticking out. So it's actually attached to the wall. By the way, this is a common symbol for like solid wall. So it's like that could be concrete or whatever, but the beam is attached over there. I see that the beam is 6 feet, 4 feet, 2 feet. It's 12 feet long and it's 1 foot thick. And so it's attached over here in some way, glued to the wall, bolted. I don't know. But it's got 40 pushing down, which of course wants it to rotate in this direction. It's got 52 pushing down at a weird angle, causing it to want to rotate in the clockwise direction. But then 60 is pushing back up. And so the question is this static? Like, did you design your cool cantilevered house so that it's static? Will the sum of the moments be, will the sum of the moments around O indeed be 0? If they're not, you're a bad engineer. Now, what your problems are going to be in your assignment is the answer will never be 0. What you'd be doing as an engineer is coming back and saying, hey, I think I'll put a post right here. And armed with that post doing a job, then you could make it 0. Does that make sense? We'll get to that later on. But for now, we're just saying, what's the result of this? Because if we can take all this complexity, like 3 different forces causing rotations in all different directions, if we can reduce all that to just one force in one direction, then we can fix it. Do you see what I'm saying? Then we can stop it. So this is really what 4.7 and 4.8 are about. And we're really going to spend the rest of today and all of Thursday talking about this. So let's just dive in. Sum number 1. I don't know why. The sum of the forces in Y. I'd like to give you a little bit of time to see if you can, I don't know, get this first. So this will be the only problem we do today. We'll finish this problem and we'll be done. Let's see if I already did it someplace. So there's 3 things we got to deal with here. The force, sum of the forces in X, the sum of the forces in Y. Notice we don't need the sum of the forces in Z because this is a 2-dimensional drawing. And we need the sum of the moments. We just got to look at what all of that amounts to. So let's see, that seems pretty straightforward. So I see 40 going down. That's pretty obvious. What about 60? Are you super clear now that you can't just say plus 60? Because what you've got to do is break 60 into its component parts. So 60 is really this hypotenuse. So since this force in Y over here, and I see, I'm going to, just to be a little clear here, I'm going to call this point A. So that way I can say force of A force at A in the Y direction. I can't say force of Y because I've already used that someplace else. But couldn't you say, I hope you're bored by this now, that the sine of 40 degrees is opposite, which is force of A in the Y direction divided by 60. So if I take 60 times the sine of 40, sine of 40, I get 38.567. So I'll call it 38.57. And again, I'm minding in my head that these are all pounds. I'm just not writing it down. Not writing pounds down. And that is up. It's vertical. So that's actually positive. And then don't I do the same thing over here? Switch to blue. If I call this point B, let's put it over there. Notice this is easier. Do you see it is easier that you were given the angle not as an angle, as a degree, but you're given it as a ratio? Took me a while before I agreed with that statement that it's actually easier. So if I say force of B in the Y direction, because of these proportions, it's 12/13 in the Y direction. So the force of B in the Y direction is 12/13 of whatever the force is. Oh, it's 52 pounds. $52 divided by 13 is 4. 4 times 12 is 48. So that's why I picked 52, by the way, because it came out nice. And that's down, so that's actually negative. So there's my sum of forces in the Y direction. Negative 40 plus 38.57 minus 48. Notice it is not equal to 0. Rather, negative 49. Do you agree as an engineer that's not good? Ultimately, we want that to be 0. What this tells us is the beam is falling, unless you come up with something to stop that. Secondly, we need the sum of the forces in X. Same process. Notice the 40 makes no contribution in X at all. It's straight down, so there's nothing coming from the 40 in X. But the other two forces are pushing against each other. 60 to the right and 52 to the left, so they're pushing against each other. So this would be the force of A in the X direction. And that would be 60 times the cosine of 40. So force of A in the X direction is 60 times the cosine of 40, which I'm getting 45.96. And it's pushing to the right, so that's positive. Cool. Notice carefully where I'm drawing these arrowheads so that you're making this work. The arrowheads are always pointing at the same point. They're pointing at the same point. That's where these forces are acting, is at point B. And so that'd be 5/13 of 52. So force of got excited and started writing that in the wrong location. Force of B in the X direction is 5/13 times 52, which is 20. And again, it's the picture that tells us that's actually negative. So again, not equal to 0 yet. So the force in X total is positive 25.96 pounds. So I just took these three complicated forces pushing every which direction. When there's lots of forces acting on something, you got forces going everywhere. And I just reduced them all. I can like throw all those forces away now and just say, oh, there's only two. Here's the vertical, here's the horizontal. Isn't that what we've been studying already? Like, that's not new. Now, what about rotation though? And notice I did say acting at point O up at the top, replace the forces, acting at point O. So now let's see if we can finally, or third, figure out the sum, not of the forces, but of the moments. And it's good to say around O. And we're going to need every one of these answers we just got, like back over here. We're going to need all those forces, the 20, the 45, the 48, the 38. We're going to need all of those. Every one of those forces. There's 5 of them. Do you see that? Stare at it with me up here. Because we need these forces to be vertical and horizontal. So I got 40, and then I've got this force here, which I should have labeled force. I guess I'll relabel it really quick. It was labeled over here, but that's the force of A in the Y direction. I've got that pushing up, and I've got this force of AX pushing horizontal, force of BY pushing down, force of BX pushing horizontal. It's like all 5 of those are causing rotation. Notice point O is actually in the middle of the beam, and the beam is 1 foot thick. So does it make sense this force of A of X right here could easily be forgotten in this case, but there it is. Force of AX is acting in that, and that's a distance of 1/2 foot away. And notice the same is true for the force of B of X, like it's acting in this line. So if I move it over here, like both of those forces have a perpendicular distance of 1/2 foot. So every one of those 5 forces up there are all going to have a distance. They're all a distance away from O. Nothing is pointing straight at O. So all 5 of them are going to count in the sum of the moments here. So let's get rolling. So I've got 40. 40 pounds. Notice perpendicular to 6, super easy. 40 pounds, 6 feet, easy. Is that positive or negative rotation? Staring at the picture. You should see it as pushing it around in this direction. So that's causing clockwise rotation, which we call negative. Again, you cannot afford to get that wrong. Great, there's one. And while we're at it, isn't the force of B in the Y direction also causing that same rotation? Except notice it's further away, 6 feet, 4 feet, 2 feet. It's 12 feet away. And force of B, I haven't figured out the sign yet. Force of B in the X direction, as I said a second ago, isn't it 1/2 foot away? Do you see in the picture that because it's up here, it's causing rotation in that direction? It's actually causing clockwise rotation. So that's actually positive. Now I'm down to A. Let's keep going. So I've got the force of A in the X direction, also a distance of 1/2 of a foot. Notice, at least the picture shows, it's a couple moments. In other words, that brown and red force are both causing clockwise rotation. Now it's not a couple because they're not the same size, but they're both causing it to want to rotate positively. So that means this is also positive. And then finally, lastly, force of A, Y, right here, pushing straight up, a distance of 10 feet away. That's causing also clockwise rotation. Do you see that? All those added together. Again, if they add up to 0, then we say, great, that thing isn't wanting to rotate. Awesome. So let's see, 40. I think I'll not rewrite all that. I think I'm going to go back and throw those numbers in. So what was the force of B in the Y direction? That was 48. And by the way, this is kind of a cool way to do this, like on a test or something, because you can still see the force of BY and it makes you slow down and so forth. But you're going to get these wrong just because there's so much going on. So it's like, it's really important as an engineer to learn how to think slowly and systematically. And notice it's turning out to sort of save my neck that I actually labeled this so carefully. I called it point A and point B, and I was able to call each of the forces, force of A and Y and force of A and X and so forth. That's probably going to keep me from making a stupid mistake here. So now I'm just going to go back and replace all these forces. What was the force of B in X? That was 20. And the force of A in the X direction, I'm looking back at all my notes. There it is, 45.96. It was labeled so carefully that I can see it. 45.96. And force of A in the Y direction, there it is in red, 38.57. Now I can just plug and chug. Be very careful. I love graphing calculators because I can see every number I type. So I can make sure that I'm typing what it actually says. Minus 48 times 12 plus 20 times 0.5. By the way, have you seen the convention that some people use? They don't say 0.5, they say 0.5. Do you understand why people do that? Why do people say 0.5? Why do books always say 0.5, not just 0.5?
You don't lose the decimal place and
Exactly. So you don't lose the decimal place. So plus 20 times 0.5 plus 45.96 times 0.5. And finally, plus 38.57 times 10. If I didn't screw up, I got negative 397.32. And all of my units were a pound times a foot. So this is foot pounds or pound feet. Doesn't really make any difference. And again, it's kind of cool to point out, oh, negative, that's down. Oh, that's kind of cool to just remind myself or speak English and say, oh, by the way, that's clockwise. Would you agree I have successfully reduced all three of these forces and kind of simplified it so that now I know how badly it wants to rotate and I know how badly it wants to fall down, so translate vertically, and I know how badly it wants to translate horizontally. So it wants to go down with 49 pounds. It wants to move right. It's being pulled away from the wall, 26 pounds, and it wants to rotate almost 400 foot-pounds. So I know the result of this. And now as an engineer, you can go on and stop that. Now, what did this question ask? Am I done? Replace the forces acting on the cantilevered beam by an equivalent resultant force and couple moment, acting at point O. Specify where its line of action intersects the midline of the beam from point O. What? So this is where it gets really cool. Not only do we figure out all these forces, but we can actually figure out where they're acting. So, where are they acting? What does that mean? Well, better switch to a color we have not used. Let's switch to black. So in one sense, we're done. Like, we figured out a lot of stuff, but let me just show you something even sort of cooler. You can actually figure out where this is acting. In other words, where is it actually behaving? Right now I'm guessing. I have no idea where this is. And so I'm going to pretend it's acting right there. And I'll call that point R for resultant. Now, would you agree that as a result of what we just figured out, that at that point right there, we just saw it was 49.43 going down? You agree with that? And secondly, that it was pulling right at 25.96, which I think I will. Dang it, what are you doing? I'm going to move that down a little bit. So I'm going to choose to draw the arrow on the left side pushing as opposed to over here pulling. It doesn't make any difference, but I'm just writing it over there. So that's 25.96. And again, I don't exactly know where that is. I don't know if that's where it is, but watch this. How could I figure out where it is? I'm going to give you a second to think about that. How could I figure out where that is? How could I use that rotational answer right there? Now, what I've done is I've reduced all three of these forces. The forces are all gone, and the only thing left is this black force now. Yet, isn't the rotational moment still conserved? Like, isn't it still got to be 400, negative 400? How could I use that? Watch this. Would you agree that this is some distance right here? I don't know what that distance is, but wouldn't it have to be true? Would you agree that the 25.96 is causing no rotation at all because it's pointing right at O? It has no distance. Do you agree with that? However, the 49.43 is. So would you agree that it must be true that 49.43 times that distance D has to be the entire rotation? Do you agree with that? And by the way, that force is downward, so I should call it negative 49. So if I take 397.32 and divide by 49.43, I get a distance of 8.03. D is 8.04 feet. That's where it's located. So by considering not just the vertical desire to move up and down and the horizontal desire to move, and also the desire, by considering all of them together, I can actually see where that force is actually acting. So I just got rid of all three forces and replaced them with just one force, and I know where it's acting. So is my picture correct? Was my guess correct as to where this is located? Notice the 6 feet right there. No, it's 8 feet. So my location isn't good. So I won't erase that. I'll just say kind of actually let's say R is actually here, 8 feet, be right in there somewhere. So I know where it's located. And then isn't this cool too? Like let's even do one more thing. If it's right 25.96, and as it turns out, down 49.43, couldn't I then calculate the resultant kind of vector from that, like as a magnitude? Again, you tend to not need to do this. It's kind of nice just to have them as 25 and 49. But if I wanted to find this angle right here, couldn't I do it? And if I actually wanted to find the resultant force, couldn't I actually do that, the magnitude of that resultant force? Because of the picture, notice because of the picture, I didn't have to call 49 negative, like I drew it in here as downward. So when I did that, I got 55.8 approximately. And then of course, theta would be equal to the inverse tangent of opposite divided by adjacent. So theta, second tangent of 49.43 divided by 25.96 is 62.29 degrees or 62.3 degrees. Because of the picture, notice I don't have to say anything, but if I did want to say something, I'd have to say rotated clockwise from horizontal. Does that make sense? Or if you use the conventions of trigonometry, you just say negative, because negative is how you say clockwise rotation, but the picture kind of tells the whole story. So then just to kind of give you a chance to soak on this for a minute. Ultimately, then I'm saying this beam here ultimately has this force acting on it. So if I come out there to 8.3, 8.04 feet, and then I draw my 64-degree angle in there, and I'll try to draw that at least reasonably accurately. My 62.3-degree angle, and my actual force is 55.8 pounds. Does it make sense? That was a lot of complicated forces acting on that cantilevered building that wants to cave in, and now I've just reduced them all. I sort of know the center of mass, if you will, of where that force is acting at. And I know how much force it is, and I know what direction it's going. And now as an engineer, I could work backwards to stop that from happening. That's kind of cool. You able to track with all that? Do you feel like that's a lot of calculations to make, but thankfully it's not 3D, so I don't have to rely on mnemonic devices and determinants to figure out these rotations. I can just see them in action.
So I have a quick question.
Go ahead.
Because now you know the distance, the angle, and the force. So we just need to go find the strong enough post or whatever and place it at that distance at that angle, right?
That'd be ideal. Yeah.
Okay.
Now it doesn't mean you have to do it that way, but it'd be ideal.
Okay.
Nice job. And you know, in a sense, sort of the cooler thing it might mean would be, I guess I'll erase this because it's going to make a mess of this, but does it make sense that you could come back here and attach a cable in this direction back to the building, if you will? And notice I knew exactly what angle to attach it at, and I just have to make sure the cable won't snap with 55 pounds on it, right? So I can't use string. I've got to use something at least reasonably strong. And so it's pulling in the perfect direction to stop that from happening. And so effectively the arrow that I draw on this is going to stop the rotation. Do you agree with that? That's going to stop the rotation because it's pulling exactly the opposite direction at exactly the same point. So this is also going to be 55.8 pounds, right? So it stops everything. It stops vertical, stops horizontal, stops rotation. What do you notice about those two 55-pound forces? They're a couple moment. Aren't they parallel to each other in the same exact size? Like that's what's going to stop this from happening. So in our case, we're just stopping it. Hey, look, I found the resultant. So notice if you take the distance between those two forces, it's 55.8 pounds times 0 because they're not, you know, one's over here and one's over here. Those are a distance apart. These are straight lined up with each other. So no rotation. Sweet. And obviously these have the exact same force pulling in exactly the opposite direction. So it balances X's, Y's, and rotation. Sweet. Now this thing doesn't fall down. Love it.
Then in real life, you'd have to like make it stronger so it correct for snow, whatever other forces you had.
Yeah.
Mhm.
So what I want to do with this tomorrow is I'm gonna actually show you some of those real forces because this problem and all the ones in your book are so contrived.
Yeah.
It's like, you know, what is that? Like a 40-pound bird? What landed on there? What, you know, why would the 52 pounds be, where did that come from? You know, what is that? These are just getting stuck on there, but I'd like to show you a little bit about, because of what I do, drawing house plans on the side, I'd like you to see where these forces come from a little bit so that you're, because an engineer is not going to be given a drawing like this. Does that make sense? You have to be the one to define that. Does it make sense the 40 pounds could be the weight of the beam? Doesn't the beam have weight? The only problem with that is notice it's not in the middle. If that was the weight of the beam, does it make sense it'd have to be acting? Actually, it is in the middle. Never mind, I lied. Isn't it right in the middle of the beam? It's 6 pounds, 6 feet on the left and 6 feet on the right. So it's right in the middle. Like that 40 could be the weight of the beam itself. What could that 60 be? Well, I guess like in that cantilevered house example, remember that pipe that was kind of pushing up from the bottom? Like that could be part of your solution. Like in this case, it's not part of the solution, but that could be part of the solution. What's that 52 pounds out there? Now it's acting at a weird angle that makes no sense, but does it make sense that could be the people that are walking on it, or it could be the snow? Because there are what's called in engineering live loads. Live loads are, well, they're alive, they move around. So snow is a live load, comes and goes. So you do have to design it to be strong enough that if it snows a foot deep on it, then that cable still doesn't snap. So that's what you're designing for, is kind of worst case scenario. Does it make sense if the cable is capable of holding 55.8 pounds, as long as I have all the forces correct, it won't break? But if snow added a bunch more weight to it, then I just make the cable stronger. That way, if it's pulled on harder, then the cable still doesn't break. So it's not as though the cable's capable of resisting the 58 pounds. It doesn't mean it always is pulling 58. You see what I'm saying? It just means it's capable of it. So we'll get around to this a little bit tomorrow because I want to kind of expand your understanding of this a little bit more. But there's a thing called live load, comes and goes, people, snow and so forth. But there's also dead load. Dead load would be the beam itself because it's not changing. It's dead. It stays there. It's always 40 pounds and so forth. All right. I think I should let you go think. So you should be able to finish the 4.5 questions now. I only did one example though, so that doesn't necessarily mean you have everything figured out, but that might help you finish that section. And then you might want to start into 4.7 and 4.8. Actually, if you really understand this example I just gave, the 4.7 and 4.8 questions are now doable, but we're going to do some more examples tomorrow. So let's see, did I already download that? I'll show you real quickly what we're going to start off with tomorrow. This is the kind of questions you'll see in your book. So that one's straight from the book. Replace the loading system acting on the post by an equivalent resultant force and couple moment at point A. So we're just going to practice a little bit more, and then we'll jump into the really cool example that I have prepared for you. All right. Stay after, get out of here. See you tomorrow or Thursday.
Thank you.
Thanks, Doug.
Thank you. My pleasure. Ian, are you? Ian's gone. I was wondering if I got any homework from him.
So let's say if I, John wants to build a deck, right? And it's gonna have a weird shape. So I need to define the center of mass first, all of the dimensions, right?
Yeah.
And after the weight, the dead weight of the whole materials he's using, all the wood, everything together. Better probably a little bit overestimated, right?
Well, what engineers do, like in your case, if you're cantilevering the deck out over the water, which kind of means if you get it wrong, people really get hurt.
Yeah.
Civil engineers will take, let's say your resultant force, like you calculated the snow and the weight of the wood and the weight of the people and all that totaled 1,000 pounds. So that's like worst case scenario, there's 1,000 pounds on this deck and it acts, right here. What engineers do then is they say, okay, it's now 2,000, like they double it.
Okay.
That's if it's a civil or a public project. For any old garden variety project, like some person's building a chicken coop, they multiply by 1.5. So it'd go from 1,500, it'd go from 1,000 to 1,500. So then they would do all their calculations and concrete and cables and all that stuff to hold 1,500 pounds because there's a 50% factor of safety.
Mm-hmm.
So yeah, it's kind of funny because you're sort of careful to get everything exactly right. And then you say double it, all of a sudden it's like, whoa. But you can see why. You can see why that's the case.
Oh yeah, especially here. Is that drop down to the water?
Yeah, like if there'd be people that would die from that. I mean, maybe not you, because you're young enough, you just land upside down in the water or whatever, but like your mom or my wife might die from that.
Yeah.
So yeah, I mean, that's an example of a place where I would double it. I'd do all those forces and then double it. The other side of it is remember the materials, like, because you don't have a whole lot of control over the materials. In other words, I mean, are they as advertised, and what if they're sitting there for 10 years? At some point they rot. So, you're sort of building in a lifespan, as well, since metal rusts and, all that sort of thing. You're building in a little bit of factor of safety for people screwing up, or, they cut the board at the mill, but it wasn't the size it was supposed to be. So now it actually isn't as strong. And you're like, well, that's okay. I built in factor of safety. So makes total sense.
So, and you saw the location. Is it better to just like put the whole support on the bottom or have a cables shooting up?
Yeah, that's a good question. Let me,